Okay, the process is a two-step process. The first step is a bridging step, and the second is a Viafill, similar to a blind Viafill process. I'm going to talk a little bit about the capabilities. It's not for all boards. There are a lot of limitations around the aspect ratio of the hole and the diameter of the hole, and we'll talk a little bit, if time allows, about some of the applications that this has been looked at for. Okay. One of the big drivers for this is miniaturization and managing heat from the ever more powerful devices that are mounted on these denser circuits. The drive for copper fill is really down to the pure copper being able to manage heat away from devices better than paste, some of the plug-in paste that we all know. There's going to be quite a lot of simplification in build, particularly we're seeing this in Asia, where there are a lot of very high layer count, very thin boards, and you can get away from a multiple bond with stacked vias by filling these vias in a single process. It's a two-step process. The initial part of the process is a bridging process that requires really quite sophisticated equipment. I'll talk a little bit more about that. And then once you get to this stage, you've then got essentially a blind via. And, I think the way we fill blind vias is pretty well understood, and the limitations of filling blind vias as well. Benefits of the through-hole plating are reduced manufacturing steps. But really, it's a technical thing. It's that improved electrical conductivity may be important for power, for carrying power. But the principal reason is the third one listed there, which is improved thermal conductivity. It's very important for us to not mislead people that this isn't for everybody. This is going to be quite demanding technology. It's easier to fill X holes and thin materials. Very high aspect ratio. Find it eventually. There we go. High aspect ratio holes are always going to be challenging to fill with an electroplate, because you tend to get a void here, and that's a disaster for reliability. Some sections of some work that we've done in development. Actually, bridging a hole is relatively easy with the right equipment, with the right chemistry. To bridge it is really very easy. It's probably more down to the equipment than the chemistry. There's some quite specialised equipment involved in it. this is a view looking down onto a panel in the tank. The blue is the acid copper electrolyte. We use inert anodes for this. One of the keys to it is these things, which probably don't show up very well in the photograph, but they're basically banks of inductors. And one of the key pieces of equipment is very, very high agitation and a lot of small inductor type nozzles to get very high solution movement across the surface. We have on a typical panel, we would probably have 60 inductors either side. We would have very high solution turnovers. On a 200 litre demonstration tank, we're turning it over roughly 100 times an hour. We do have cathode rod agitation, but the key to this is this agitation, very, very high agitation. So I've already mentioned that we run insoluble anodes. These are typically mixed metal oxides, iridium oxide type anodes. Those are expensive. You know, this isn't cheap equipment, and it's certainly involves quite substantial investment to make this process work. It's very important to get this solution jetting onto the cathode surface evenly. And typically we run a fairly conventional spacing between anode and cathode of around 100 millimeters. It does require cooling. So another cost. You've so much energy going into it from the pumps that the temperature of the solution will rise. And like with most acid coppers, high temperatures are bad for the stability of the organic materials in there, the brightness and the inhibitors. And the other really important piece of equipment is the rectifier. It's quite a sophisticated pulse rectifier, and the waveform and the bridging part of the process is key to success. You need really quite sophisticated rectifiers. A regular pulse rectifier won't succeed in this. Essentially, once you've bridged the hole, you've then got microvias on the blind vias on the surface, and this is really the limitation of the process at the moment. If you've got lots of different hole sizes, you're going to have lots of, you'll be able to bridge all the holes very easily, but to then fill the different shaped blind vias, it is the challenge and is really quite difficult. So typically boards with just one size of hole or a relatively narrow variety of hole sizes will be successful in this. There isn't a magic additive that we've developed so far that will allow us to fill a wide variety of blind vias in the same process at the same time. We've done quite a lot of work on this. and we're looking at the blind via size around 75 by 75 microns up to about 350 by 300. One of the problems with the larger holes is because you're trying to fill quite a deep pipe, you end up with a lot of copper on the surface. That can be an issue for design. This is a fairly typical Viafill process, looking at the blind vias. You absorb materials, organic materials onto the surface that encourage the plate, or the build-up of plate in what is essentially a low current density area of the board. And the balance of these additives controls the fill. You'll have a different balance of additives depending on the size of the blind via that you're looking at filling. That's what gives a limitation to this kind of process. This is an array of hole diameters and panel thicknesses, and this is the operating window as we've defined it at the moment. It is part of an ongoing development. It's something that we're continuing to work with our customers and in R&D. Typically, the really sweet spot is around hole diameters of around quarter of a millimetre and panel thickness of a little bit more than that, around 0.3, 0.4. That's the really sweet spot. You get out to board thicknesses of a millimetre and you're really struggling to get that fill. So it's only going to be something of interest to people making thin devices, where thermal management has to be more of an issue. There's some sections that probably don't come out very well. Bill, will we be able to distribute this?
Yeah.
Yeah.
If that's okay with you.
Yeah, that's fine. A whole array of holes. You can see, you might be able to pick out, certainly if you're nearer the front, the two groups of copper. That bit there is the bridging copper, and then you've got the blind via filling there. There you've got a higher aspect ratio hole, and you've got those voids. That's going to be a problem. Generally, a lower aspect ratio hole, a wide hole on a narrow surface is relatively easy to process. And again, an array of test results. Most of this work has been done in the US at our development center in Connecticut. Again, it shows quite a wide variety of holes. It shows what the process is capable of. but I must emphasise that it's really important not to understand that this is limited around the variety of holes that can be filled at the same time. These will all have been filled with different recipes, particularly on the second step. Again, some more test results, some more sections. As I said earlier, the laser drilled X holes are probably the easiest of all for us to process. These are typically very thin materials as well. Don't see too much of this material or these types of boards being manufactured locally. The mobile communications boards, mobile phone boards manufactured out in the Far East is probably going to be a big market for this technology. Worth pointing out that the cycle time on this, to fill those, we're looking at around 75 minutes. So it's a reasonably quick process. And here we've ended up with 21 microns on the surface, which is manageable. Just some data. Again, if we circulate this presentation afterwards, you can read the figures. But there's some good information. Quite a lot of work has been done to validate this, to make sure that what we're actually producing it gives not just the fill that we would like to look at, but also some of the deposit characteristics that are required by the end use. It is some solder shock testing, as you would expect. There's no loss, no cracking, no loss. Over quite a wide range of bias there. This isn't badly out of focus. This is an X-ray, and what we're looking for here are voids and issues within the fill. And again, on the testing that we've done, we've got pretty good fill. So, in summary, the copper fill process gives us improved reliability over paste. Two-step bridging process gives us the ability to fill a really wide variety of holes. It achieves fill on thicker substrates, enabling us to maybe move away from a sequential build. We claim that it has reduced cycle times and costs. That's dependent on what application it's for. The equipment itself is going to be require quite a substantial investment. in both the tank and the rectifier, so there is a significant cost in that. This is work that's very much in development and is being targeted at specific applications for specific customers. Some of the areas we're looking at are LEDs, where heat management, thermal management, some military, some aerospace, and some automotive where we're exploring the current carrying capability of some of these thicker boards. Just a couple of reference slides. This is data from one particular application where 70% of LED failure are a high junction temperature. 20% of the output converts to light, and 80% approximately converts to heat. And if we can remove that heat away from the LED as quickly and as efficiently as possible, that's where the reliability will come in. Some thermal imaging showing the temperature and how localized it is around that LED unit. That concludes my presentation. If you have any questions?
You mentioned earlier that the range of hole diameters was fairly narrow in terms of minimum maximums. Is that as a result of the equipment, availability of the equipment, or
No, it's you can set your equipment up to fill and bridge and fill a specific range on a particular board. Where you run into difficulties is if you're trying to bridge and fill small holes and large holes on the same panel. The first step in the bridging bit, that works reasonably well across a wide range on the same panel to the same recipe. The difficulty is you then have a blind via of a variety of sizes and depths, and to fill those successfully without building a lot of copper on the surface, that's the limitation of it. But if all your hole sizes that you're trying to process are similar, with different recipes you can cope with a different range, but you would need a different recipe.
On a similar subject, if all of the holes are the same diameter, the same aspect ratio, but there are higher and lower densities of holes with different parts of the panel you're plating, you have, as a result, you have different current densities for different holes. Is that a problem? Do you find that some of the holes are plated well and some are left with voids along the
Very much so, yes. And that's why the equipment uses this enormous amount of agitation to try and widen out that window as much as possible. The agitation on these tanks, we've a test unit in Germany that I went to see a few weeks ago, and it's a relatively small tank with two enormous pumps to the side of it, and my instinct was I don't want to be anywhere near this when they switch that on. You know, there's enormous flaws things, and that I guess breaks down that diffusion layer right on the cathode surface, gives you a very uniform distribution. You're not relying on that diffusion layer, which gives us most of the problems on a variety of current densities. The peak forward currents on this are enormous, and that's why we have to use mixed metal oxides and replenish with copper oxide. So there's a lot of the equipment that I've just not got time to go into now that gives us a reliable, reproducible process.
Okay, any more questions? Okay, thank you very much.